pleasure to introduce Pablo, which is here from Spotify, and will tell us how they've been using Kafka and Storm to process quite large amounts of data. Give a warm hand of applause to Pablo.
Thank you very much. Have you been having fun? Cool. So let's try to keep it like that. So my name is Pablo Barrera. I work for Spotify. I've been working with them for the last 2 years, and I work as a tech product owner. I'm responsible for the data transfer platform, the real-time platform, and also the batching processing platform. So Hadoop, Storm, Kafka, all those things. Today I would like to talk to you about how we do the real-time data transfer and processing, and also how have we done it reliable, because that was one of the requirements that we had, and what we learned by doing this. What are the things that we have learned? I hope you know about Spotify, that you hear this name before. We are basically a music service. We try to provide the right music for every moment. These are the official numbers that we have in the web page. That is just to give you an idea of the size of Spotify. I guess the first thing that you will spot is that the numbers are huge. I mean, we have millions of users. So that is related with the kind of things that I do. I work in scalability problems. So I belong to something called the IO tribe, or Infrastructure and Operations tribe. And there we work building the infrastructure that holds Spotify, that supports all the features that we have in the platform. For me, Spotify is a tech company. We work in a really big variety of problems. From cloud computing to machine learning, we are focusing real-time data analysis, or in building, mobile applications. Today I'm going just to focus in one of the tasks that we do, that is the data transfer and the real-time processing. So I would like to start just explaining what is the problem we want to solve, what is the thing that we want to do. It's actually quite simple. So you have somebody that is listening to music somewhere in the world. Every single time that she does something, we want to know it. So if you are listening to Justin Bieber, we want to know it. Not because we want to figure out who is listening to Justin Bieber, but because every single time that somebody listens to something, we need to pay to the label of that artist so they can pay the artist. So for us, it's a strong requirement. For doing that, we have a Hadoop cluster. That Hadoop cluster lives in London, so it's a Hadoop cluster. I think we have more than 500 nodes for the Hadoop cluster, and we are continuously growing it. And our goal, the only thing that we're trying to do is to send the data from your device to this Hadoop cluster. So that should be easy. I mean, how hard it could be? It's just copying data, right? It sounds simple. But we have found that it's quite difficult, that it took us a really long time to solve this problem. So in order to show you why is this difficult, let me start with a simple approach, what we call the naive approach to this problem. And of course, this is a naive approach, so it's the first one that we tried out. So every single time that you receive a message, you just log it using a standard logging library like syslog. So the log gets into a file, then you get the file, copy to another machine using secure copy, then you have all the files into one single host that we call the log archiver, and use something similar to wget or call to send into Hadoop, maybe using a web proxy or something like that in order to allow distribution and having several sites. And that's what we did. And more or less, it's quite simple. I mean, this is just 20 lines of bash code, so it's not simple and it's not difficult at all. However, I would like to turn to two pieces of this problem that are the secure copy and the call, or wget. So those are the bottlenecks of this system. They are difficult to parallelize. And when you want to send a lot of files and not just one file, you actually have a scalability problem. How do you solve a scalability problem with these tools? It's simple. You put in a for loop. I mean, you just, for every single host, every single file, you copied it, and then you copy it again to Hadoop. The sad truth is that this is actually true. I mean, this is what we did. And we have been doing that for a really long time. And yeah, looked like a good idea when we tried out, but after a while we realized that it is not a good idea. It works when you have a little amount of servers, but when you keep growing, you actually have a really big, serious problem. So this is the problem that we have right now. We have thousands of servers in 4 different data centers in 2 different continents. We have to support millions of users, and we produce 10 terabytes of new data a day. That is something that you don't want to handle with a for loop. So you need to do something better. So what are the needs of this problem? So we sit together like 1.5 years ago and decide, okay, what is the problem we actually need to solve? And we come with this requirement. The first one is that we need reliable delivery. I've said we need to tell Justin Bieber or Lady Gaga or Madonna how many people is listening to them, so we can actually give them an invoice and give them money for that. So we cannot afford losing messages. We also want to have a fast data delivery, at least faster than what we used to have. This for-loop solution took like 3 to 5 hours to deliver data since the moment that you produce something until it was available in Hadoop. So it was a really long time, and for some applications it was not good enough. As we were trying to replace the system, we also tried to figure out if it is possible to subscribe our applications to a given service. So you are reading messages for a given feature. I am only interested in messages from this feature or from this server. That will allow us to work in applications that just consume that data without consuming everything. I mean, without consuming those 10 terabytes of data. So that was more a desire. We also need to have a really low CPU overhead. So we have all these I think it's 6,000 servers around the world, and some of them are really, really loaded. So we don't want to add more load to those machines. So if we can do it lightweight, it will be great. And the last but not least requirement is backwards compatibility. So this was a critical system in the middle of our pipeline. If we want to replace it, we want to keep backwards compatibility, so we don't need to change everything. So this was the problem we wanted to solve. So we started to evaluate options. As we want to keep reliable delivery, we started with messaging system like queuing system, similar to AfterMQ or RabbitMQ. It turns out that they are really, really slow. I mean, they are good for the use case, but for sending this amount of data, they were just insane to use. So we decided to stop using them like 5 minutes later to start using them. Then we started to use Flume. We keep Flume in production for around half a year. It more or less worked, but it was not great. So we found some problems, especially in performance with Flume. We have experience with that, but at the end we also decided to skip it. We also evaluated on paper other alternatives like Scribe, but we decided to go for another alternative that was Apache Kafka. Apache Kafka is a distributed pub subsystem. It provides high performance, it has a low overhead, it's written in Scala, that for some people is a feature. It's open source. It was developed on LinkedIn that used to have similar problems to the ones that we have. And now it's an Apache project and it has a huge community. And that was really good news for us. So we started to use it. The things that we liked the most were that it provides an easy way to read at least one time every single message. So without investing much, we can actually be more or less sure that we are consuming everything. So that looks like a nice feature to have. Also, the complexity, it was really, really simple. I mean, the overhead was tiny. Independently of the number of messages that you have in your broker, in adding a new message or reading a new message has continuous time and complexity, so it was great. And what we liked the most is that we were network bounded. So it was not the CPU, it was not the memory, it was not the Java machine, it was the network or bottleneck. So we could do nothing better. We just need to go to the data center and chain the wires and put fiber or something. So it was a really good feature. I guess that most of you don't know much about Kafka, so I'm going to briefly explain how does it work. Kafka it's similar to a queue system or a pop-sound system, so it has three pieces. It has a producer of data that sends the data to a broker, it puts it into a different topic, and then a consumer can subscribe to that topic and read the data. One of the differences that it has with other queuing systems is that the broker doesn't keep track of who reads the data. So two consumers can read exactly the same data. Actually, your consumer can read twice the same data. By removing that complexity, so not keeping track of who is reading, the broker is super simple. The only thing that you do is get data, put it into a file. When somebody asks for data, give you the file, and you do nothing else. So it's super fast. It also provides nice distributed features, so you can have multiple consumers reading from the same topic and balancing the load. So one reads half and the other reads the other half. You can read from several applications the same data, so you can do different stuff like your real-time application and other real-time application. So it was a really nice alternative for us. In top of this, you also have Zookeeper. So there is a Zookeeper cluster keeping the synchronization between your producer, your brokers, and your consumers, although I haven't added to this picture. So everything sounds really, really good. So what is the problem? It has actually several problems. For example, it's not reliable. That was one of the requirements. It has no replication. So if one broker dies, everything that you have in that broker is lost forever. So you don't send the same data to two places. And it requires manual tuning, but we were expecting that. I mean, for the size of the application that we were trying to build, manual tuning was granted. So we continue with it and decide, okay, let's build this and put it in production. Right now, we have been using Kafka, I think, for around a year. We are really happy with it. It's the key component for our new log delivery system. We also use it for the real-time applications, and we have started to explore other applications like messaging systems or things closer to PubSubs. We used Kafka 0.7.1. It's not the latest version of Kafka. The latest version of Kafka is 0.8 that was released like 3 months ago, but we have been running this in production for much time. So we just took the one that was stable when we started the development, and we never found a reason to move to the next one. And we use Java 7. By the way, I think I haven't mentioned it, but if you have questions and you want to interrupt me, please do it. Otherwise, I will have time at the end. You want to do the question later? Sorry about that. So this is the infrastructure that we started to use. However, as I said, it didn't meet all our requirements. So we need to develop 2 things on top of that. And that's when the things get interesting. The first thing we tried to do is an end-to-end reliable delivery. So reliable delivery wasn't a strong requirement for us, so we need to find a way to do it. Second one was a compression and encryption service based on Kafka, that I will talk about that later. So let's center in the end-to-end reliable delivery. Reliable delivery was the thing that we needed. Remember the size of the problem, 10 terabytes, 3,000 servers, so it's going to be tricky, but we will try to do it. So what do we have? We have a bunch of hosts with syslog files. I mean, this is the bad word compatibility thing that we don't want to mess around, so we are going to keep using syslog files. And in all those hosts, we add something that we call the Kafka syslog producer. It's basically a daemon that keeps tracks of those files. Every single time that you add a new line to those files, that is a new event, we take it and send it to the Kafka broker. We added that event into a topic with the service name. So all the machines that are running the same service send the data to the same topic, so you can read it together. Then we read the data from a Kafka syslog consumer and forwarded it to Hadoop. This is basically any solution that you can think of with Kafka. I mean, this is the basic Kafka. You just have a producer, a broker, and consumer, and that's something with the data. In top of this, we added something extra. That it was, once the data is in Hadoop, we send it back to the broker and put it into a different topic that is just hacking. So we tell the broker, okay, we received this message, and now it's written to Hadoop. then the producer can read it and figure out what he needs to send back. So he can figure out if a particular event has been lost or whatever. So he has some kind of timeouts until he starts to resending data. And once in a while, it sends a checkpoint that is basically a piece of data saying, your queue size, what is your health status, if you have a lot of files to send, or if you are delayed. And we use that for monitoring and also for telling Hadoop when it has enough data to start the pipeline. So with that information, we can answer questions in Hadoop like, can I start processing data today at 12? I mean, do I have enough data? So we use the checkpoint for that. With all these changes, what we changed was moving from 3.5 hours of delay to around 20 seconds. So it took us around 20 seconds from the moment that you do something in your mobile phone, you listen to something, until it is ready for consumption in Hadoop. It's just 20 seconds. So we were really happy with it. So after all these lines I put it there, I guess you are asking, is that all? I mean, it looks like a little bit messy. Yep, it's all. I mean, it's a classic reliable framework on top of an unreliable link. Think about TCP. It's doing exactly the same thing. Sends data, keep track of what it sent, and then resend if it doesn't receive the ACK. So it's not rocket science. So it should be a piece of cake, right? I mean, this is already solved. It turned out that it's not. So we developed this nice service, put into production, and nothing worked. And we were like really, really upset. So why was that? And that's what I want to share with you. So this was the solution. The producer, the broker, the consumer, and Hadoop, and everything coordinated with Zookeeper. But there is one thing that we didn't focus that much, is that our Hadoop is centralized. We only have one Hadoop cluster, and that lives in London. However, we have producers all over the world, so we have 4 data centers. We put the brokers close to the producers, but we put the consumer close to Hadoop. So this means that in most of the cases, we have a cross-site link in the middle. So the consumer and the broker lives in different parts of the world. So that link is actually a high latency link. And that has a lot of interesting problems. I want to share 4 of those problems with you. 2 of them we were able more or less to foresee them, and the other 2 were tricky problems. So the first one is that when you have a high latency link, you need to start configuring your TCP window. So you just need to increase your TCP window. This is a kernel window. So you can think of a network link like a cache. It's a memory. So you just put data there, the data is flying, and until you get the ACK, you need to keep that data somewhere so you can resend it. That is your TCP window. And you also need to increase your application window. So you need to keep that in mind, just increase the windows. If you're using Linux, you want to check how the TCP scaling algorithm works, because it has some nice features or bugs, depending on who you talk with. Once we tune the TCP window, we tried to use IPsec. Okay, we have a system, it was working, we wanted to put real data on it, so we enabled IPsec. When we enable it, the performance went to, it was really, really bad. What we found out is that the combination of the IPsec system that we were using and the firewall was really, really slow. And the problem was that we didn't have a way to tune it, because the network, it was outside Spotify, so we have an external provider. So we started to think, how can we do this in the application level? So what we did was to develop an external service. So instead of sending the data from the broker to the consumer, what we do is to add another service that lives in the same site as your broker, reads the data from the service, encrypts it, compresses it, and put it back into broker. And now we can send the data without an IPsec connection between your broker and your consumer. And then consumer can then unencrypt it, uncompress it, and put it into Hadoop. Our main focus was encryption, but compression was really simple to add. And by adding the compression there, we gain a lot of performance. So it was a really good system to put in place. as I said, we were more or less foreseeing these two problems, TCP windows, IPsec, compression. So yeah, we were foreseeing those problems. But the other two, we only found them when we put the system for real in production. So we learned something. It is difficult to test everything in testing. You need to just go to production, try stuff, see how it breaks, and you will figure out how to fix it. So yeah, we test everything in production because everything else is waterfall, right? I mean, you want to continuous deployment and all the stuff. So this was an interesting problem that we found. We put the system in production and we were releasing it like, a few hosts every single time, keep measuring how is it working, it is performing. And suddenly, when we added a couple more hosts, we saw a performance drop of 50%. So the speed that we were sending data to Hadoop dropped 50% just by adding 2 new hosts. And we were like, what? I mean, this shouldn't happen. Maybe just keep stable, but drop 50%. So we started to dig on this. What we found out is that it was Zookeeper. So Zookeeper was deciding that our machines were not connected, and then starting the rebalancing algorithm, asking the other consumers to read in a different way. Then the machine was up again, and then the rebalancing started again. So it was just a loop, continuous. So we were thinking, why is this happening? It's a problem in Zookeeper. We started looking into Zookeeper, but it was not a problem in Zookeeper. It was a problem in the consumer. The consumer was spending 20% of his time, 25% of his time doing full GCs, just pure full GCs. And that was shocking because we were not monitoring this to begin with. Why is this doing so much time just in garbage collection, and why is now doing this instead of doing this before this? So the problem was that now the system was more loaded, and instead of having temporary objects that just last for a couple of seconds, it has temporary objects that last for a little bit longer. So the garbage collector was moving everything for one generation to the second generation and then deleting everything. So it was just copying everything and deleting it, and it was just stupid. In that time, as you have the full GC, the machine was not replying to anything, so Zookeeper thought, okay, you are dead, so I'm going to rebalance and ask somebody else to do your work. And it was a really big problem. So we started to think, how can we fix this? And it was just super simple. The only thing that you need to do is actually increase your memory or tune your GC to tell young generation a little bit bigger. Now our full generation look like that. So yeah, no problem. It uses less than 0.2% of the CPU, so we are really, really happy with it.
You don't use garbage first?
Sorry?
G1 garbage?
I don't think so, but we can talk later. I have another problem that I want to share with you, that is the Hadoop replication factor. This was another problem that we only found in production. So we were sending data to our Hadoop system, everything looked fine, and as we keep adding more and more files, we started to find broken files. That is, files that were being delivered, marked as correct, but they were corrupted in Hadoop. And Hadoop was supposed not to do that. I mean, it has 3 copies of every single file, so it should be just fine. However, reading the Hadoop code, we figured out that the failure mode that Hadoop has is stochastic. So the thing that it does is, it receives the file, puts it into 3 machines, and asks you back. But it doesn't read it to disk, so it's just in memory. So you have a time that those 3 machines could die at the same time, and you have nothing. I mean, the file is corrupted. Usually, that doesn't happen. But for us, it happened because we have a lot of files, and we keep the files open for a really long time. Why do we keep the files open for a really long time? Because of backwards compatibility. We have 6 log files. They are 1 hour long, so we need to keep open the file in Hadoop for 1 hour until we change the file in syslog and start a new one. So this is a really small probability of happening, but if you are sending a lot of files per day because you have a lot of hosts, sooner or later you're going to find this broken file. And for us it was around 20 a day, so it was not acceptable. And the solution, again, once that you understand the problem, is really, really simple. It's just increase the replication factor. If this is a stochastic, just make it less likely to happen. Now we use a replication factor of 6, and it works like a charm, and we never ever found another broken file so far. So with all these problems, all the solution, we were able to just send the data, and we were super happy with it, and we managed to send data to Hadoop in just 20 seconds, and to Kafka in under 3 seconds. So from the moment that you have something in your tablet until we have the data in our backend service, it only 2 seconds, 3 seconds, something like that, independently of the site that you are sitting. So that is a game changer for us. So we started to think, okay, what can we do with this system? It's not 3 hours anymore, it's not 5 hours anymore. Can we start doing real-time processing on top of this? And the answer was yes. So we decided to move forward with Storm and start using Storm in production. Apache Storm, for those of you that don't know it, is basically a real-time Hadoop. So it allows you to create distributed applications that are simple to build and they can scale. It's open source. It's an Apache project. It was open sourced by Twitter after Twitter acquired a company called Backtype. For us, it's nice because it has really simple abstractions in the same way that Hadoop has map-run reducer. Storm has topologies, bolts, spouts, strings, tuples, and grouping. It has a really big community, so you have new version of Storm that fixes bugs, you have libraries, you have integration with other systems like Kafka. You have a lot of tools that you can use. At the beginning, we found also interesting another feature that it provides, that it does hacking inside of the real-time application. So every single time that you send something inside Storm, it keeps track of it, and it's able to resend it if something was not processed. So it promised you at least once delivery. So it will try to send everything at least one time. We thought that was brilliant because we were thinking in this reliable delivery, but after trying it, it turns out that we don't use it at all. So when we have a reliable requirement, we do it in Hadoop. And it takes 20 seconds to send data to Hadoop, so we can do batching processing every 10 minutes, 15 minutes. It's not a problem. If we want something reliable for everything else, we use Storm because it's just a second and it works. So you need to think when you want to do an application is, what kind of real time do you need? Can you wait for 50 minutes? In most of the cases you can, then you can use Hadoop and works better than Storm for those things. Then we started to think, okay, we have this Kafka system that has reliable delivery. We want to put the Storm on top of it without using the reliable capabilities, but we don't want to send the data twice. I mean, we already send the data, it's a lot of data, we're consuming a lot of resources in the network, so how can we do it? We have two requirements. We have the reliable data delivery for reporting, that one should go to Hadoop, and the low latency data for real time, that is the one that should go to Storm. So we've modified our solution a little bit like this. So we have the traditional solution, and we added Storm, and Storm reads the data directly from the same topic. So it is reading everything for a single service. And then the consumer sends the ACK back, but if the producer doesn't get it, it's going to send a retry. But instead of sending the retry to the same topic, we send the retry to another topic, and we read it from the consumer. Using this, we have the Kafka syslog consumer that is able to get all the messages, so it's reliable, and Storm that only reads the messages that are being sent the first time. We don't read the others because they are usually late. I mean, the retries has, I think it's 20 seconds. No, it should be a little bit more. It has some seconds to resend, so it's just all data, so we don't use it. So we don't even read it. So just changing this allowed us to keep the application, keeping the same infrastructure, but with two different tiers, one for reliable application and the other one for unreliable applications. So I would like to finish by talking a little bit about applications that we have to use this. The first one, of course, is monitoring. So when we were developing the Kafka platform, Spotify, we needed a monitor to figure out how much data are we sending, are we having problems, are we hacking everything, what is the queue size, and all that. We have all that information in the checkpoints, so we can just go to the checkpoints, take the data out, put it into a dashboard using Storm, and that's what we have here. That is basically just one box for every single host that we have that is for a particular service that is sending data, and we can figure out if the queue is too big, if there is problems there. It works quite well, so it allows us to figure out if one side is down. So here what we see is that all the machines, none of the machines have replied in the last 10 minutes. So we know nothing about them. Why are they not replying in the last 10 minutes? Usually this is because there is a network cut between our data center and London. We also see when the network is low or is loaded, is because all the queues are starting to be bigger. So here you see that the queue has 100,000 events. So that's a big queue for every single machine. So we can figure out several problems in the network. It's nice that we are able to spot network problems before the network people do, because we are using the network a lot. So we just go to them and say, hey, you know, you have a problem in this link. They check it out. Oh, you're right. So this tool is really, really helpful for us. After having this monitoring tool, we started to play with the platform and thinking, okay, what can we do to have fun with this? So we released the brick rolling map. So every single time that somebody listens to "I'm never gonna give you up" of Rick Astley, we plot it into a map. Maybe it doesn't have business value, but it was really fun. So we decided to put it in production, and we have it running. But the idea was simple, so it just took us seconds to put the face there. So it was really good. So we started to think, what are the things we can do to monitor? So we have other monitors that keep track of number of people listening to songs, number of accounts being created, network problems, people sharing to Facebook, anything that you can think of, and we just represent different ways. Yeah, this is basically everything I wanted to tell you about today. I think I was faster than expected, but I was expecting more questions for you. So, for your time and listening. And do you have questions? I'm more than glad to answer them. Yes?
How do you handle deduplication?
The duplication. So how do we handle the duplication? One of the things that you have in this system is that Kafka can create duplicates, and we also create even more duplicates by sending data more than once. So we have duplicates both in Storm and in Hadoop. In Hadoop, it's really simple to remove the duplicates, because as we are sending the syslog file, all the events for one single syslog file, they are going to end in the same syslog file in Hadoop. So you just have a job in Hadoop that goes through that file and removes duplicates. It's really, really simple to do. One thing that is tricky is that syslog can produce duplicates as well. So syslog by design can produce duplicates. And then you're going to remove those duplicates in Hadoop. But if you do that, then you cannot compare your files from Hadoop with the original syslog file for being sure that you're sending the same thing. So at the end, what we are doing is also sending like a counter saying, okay, this is the line number in the syslog file. So we can reproduce the same syslog file and check the health of our system. Are we doing something wrong? So in Hadoop, it's really simple. In Storm, what we do is just reading from the service topic, the one that has no retries. So usually the number of the duplicates that we have is small, and they are usually because Storm is having issues. So when you die, or your consumer in Storm dies, it starts over and can read the data. And usually there's not a big problem because you have lost memory in Storm. So you just read the same data twice. But for reporting, it's just Hadoop doing the duplication. Any other questions?
Yeah, what were the bottlenecks with AMQP messaging?
Basically, after enqueue or RabbitMQ, what it keeps is put the message into the queuing system and then keeps track of who is reading it. So once you read something, you remove it from the queue. And that's what's the bottleneck, keeping track of that. We have a lot of messages. I mean, we are sending in one broker in average time 50 megabytes per second, and it was no way to do that with NQ because you keep track of who is reading it. But Kafka does not do that. You just put it into a file, and if you read the same file, you are fine. So we don't keep track of that, or Kafka doesn't. Yes?
How many brokers do you have, and how do you manage the topics across the multiple brokers so that the clients can be aware of all the broker information coming from one topic?
Okay, so the question is how many brokers do we have, and how do we keep track of the topics across brokers?
Well, it's an end-to-end. I mean, you have multiple clients and multiple brokers, right? So you need also to be all the clients aware of all the topics. So if you have more than one broker, you have multiple clients.
Yeah. So the way that Kafka works is that when you have a producer and you want to send data to a broker, you ask Zookeeper. Every single broker is registered in Zookeeper. So the broker downloads the list of, the producer downloads the list of brokers available. We have, I think there are like 4 per site, and then we have an extra Kafka cluster in London where we centralize all the data to avoid sending data twice. That I think it has like 10 or 12 machines. Do you know, Matti?
Something like that.
Yeah. So 4 per site plus 10 in London, or 12. Once you have that list, you start sending the data to all the brokers. So you actually share your load in all the brokers. You as one producer just send to one, but if that one fails, you move to the next one, and the next one, and the next one. And by having a lot of producers, you actually have more or less the same load in all of them, because they just try to match. The client does something similar. When you start a client, you go to Zookeeper, get the list of brokers, and connect to them, and ask for the topic that you want. You can get also the list of topics that are available. So what we do is just, if the consumer checks for the topics that have a special pattern and name, and send the data to Hadoop. Because we also have other topics for other stuff, like the axe. We don't want to send the axe back to Hadoop. So we have a name convention for that. More questions? Yep.
Have you looked at ZeroIQ for the transport instead of Kafka, for example? Implementing some of the parts of Kafka in ZeroIQ or Nano messaging, I think it's called now?
We use ZeroIQ a lot at Spotify, but not for this particular problem, because we wanted to have to decouple the sending. So right now you cut one of the systems, you can actually put, it's like a queue in the middle, so you actually can do buffering there. So you have a problem in slow network, you can actually keep sending data, so you are going to adjust. ZeroIQ doesn't work as well for that, because it wants to send from one side to the other. Actually, we are starting to use Kafka as a backup for ZeroIQ. So when we are sending data to ZeroIQ, sometimes we also put it into Kafka for later consumption from another application, like for monitoring how many messages are we sending, or for resending the messages again, or for, I don't know, filtering those messages and putting something somewhere else. So we are using both of them, but for different reasons and in different places. I don't know if that answered your question. Any other question? Okay, you are. Easy, crowd. Nice. Thank you.